All right, ladies and gentlemen, in this video, we are going to introduce a topic called inscribed angles. Angles. So we're really going to kind of start to dive into specifically a theorem called the inscribed angles theorem, or the measure of an inscribed angles theorem. But before we do that, we're going to make sure we take some time realizing that we're going to first need to define some terms. You have to define what an inscribed angle is. We're going to have to define what an intercepted arc is, and then also what it means to be subtend to an angle as well. And then we're going to go ahead and dive on into how can we utilize that measure of an inscribed angle theorem. So let's dive right on in. So three terms that we're going to have to know before we go any farther is inscribed angle, intercepted arc, and what it means to be subtend. The inscribed angle is just simply what we see here in red, and it's just an angle whose vertex lies on the circle itself. It actually lies on the circle. So far, we've talked about the central angles. The central angles, remember, we're at the center of the circle. But the inscribed angle is an angle with vertex, in this case vertex B, that lies on the actual circle itself. The intercepted arc is just simply the arc that is the arc created by the intersections of the inscribed angle and the circle. So we see here, obviously, ray AB intersects the circle at point A, ray BC intersects the circle at point C, and we end up saying that the intercepted arc is arc AC right in there. Now, if we kind of see a situation like this happening, if we end up having a chord that we can connect, and I can say we can always have a chord, we can always create a chord technically, but if you see a chord, or if you see this word subtend, if the endpoints right here of a chord AC, if this chord AC has the endpoints at any of the inscribed angles intersections right on in here, that would be considered subtend. So right now, since the arc, intercepted arc right here, has endpoints of A and endpoints of C, and this chord has endpoints of A and endpoints of C, we would say that this arc AC subtends angle B, and we would say that this chord AC subtends angle B. Okay, and that just means that it has the endpoints at those particular intersections of the angle and the circle. So let's talk about our measure of an inscribed angle theorem. Now the measure of this, or the point of this theorem is to think about how can we utilize our inscribed angles to find the actual angle measures and the measures of the arcs. We're going to be able to go in both ways, because the measure of an inscribed angle here, angle ADB, is 1/2 of the measure of its intercepted arc. Okay, so ADB is 1/2 of the measure of the arc AB. ADB is 1/2 of the measure of the arc AB. Let's take a look at a couple examples here, and we can kind of use this in just kind of some basic application. So if we take a look here, it wants to know first and foremost what the measure of angle T is, the measure of angle T. So right here we see angle T, and we see that it has an arc RS that is intercepted and subtend to angle T. And so if that's the case, the measure of angle T would be equal to 1/2 of the measure of arc RS. Well, the measure of arc RS is already 48 degrees. So that means the measure of T would be 24 degrees. For our other example, it says it wants the measure of arc QR, the measure of arc QR. So let's take a look here. What do we know about the measure of arc QR? Well, the measure of arc QR is right in here. So here's our measure of QR. But if you kind of notice, you don't really see anything necessarily that is exactly, I guess you would say, representing our graph. angle, our inscribed angle that goes along with it. So let's think about what we can use to maybe fill in some missing pieces. Well, let's take a look here at this angle right in here, or this arc, excuse me, right in here, arc TQ, measure of arc TQ. Well, the measure of arc TQ is going to be 100. Well, how did I know it was going to be 100? Well, because QRT is half of the measure of arc QT right in here. Well, then let's take a look at what we know. The whole diameter TR creates our semicircle and a measure of 180 degrees. Well, if QT has an arc measure of 100 degrees, the whole thing is 180. Well, that means that the measure of arc QR is going to end up equaling, of course, the difference at 80 degrees. So in sometimes some of these situations, you got to kind of think outside the box, and it may not necessarily be that simple where we're looking at just a direct correlation like we did here or here. Let's take a look at another possible example utilizing the measure of an intercepted arc. They want to know, find the measure of arc RS. Find the measure of arc RS right in here, and the measure of the angle STR. And then it wants us to see, like, what do we notice about STR and RUS? So let's first and foremost find out what that measure of RS is going to be. Well, what do we know? From our inscribed angles theorem, we know that the measure of arc RS should be equal to 2 times the measure of angle RUS, right in here. Let's go in order, RUS. So 2 times 31 is 62. So the measure of arc RS is going to be 62 degrees. Well, let's kind of think about this. If the measure of the arc is 62 degrees, take a look what happens. The other angle, STR, that we want, STR, it is also intercepted by angle SR, or it is subtend to this arc SR right in here. So that means if they are both subtend to SR, that means this is also going to be 31 degrees. And that means that STR, angle STR, is congruent to angle RUS. And this is going to bring up what is called the inscribed angles theorem. And that will be what our next video is all about.